Okay, hi everyone. So we're going to go ahead and continue our lessons with topic 8.8. So last time we met together, we did volumes of cross sections, and so it was like pulling a book out of a bookshelf, and we looked at when the books were square shaped and when the books were rectangular shaped. Today, books can actually be triangular shaped and in the shape of semicircles. So last time what we did is we pulled out a slice, in other words, a cross section. We found the area of that single cross section, and then we found the area of all the cross sections added up by using the integral. So this time, today, we are going to do something very similar. However, we need to find area of equilateral triangles, isosceles triangles, and semicircles. So your warm-up today was a refresher on finding area of triangles and area of semicircles. So just a reminder, equilateral triangle means that all sides are the same. So we will set up finding the area using this example, and we'll see the formula, and then we'll do a couple examples based on equilateral triangles. So R is the region in the first quadrant, bounded by the graph of y equals x equals 4, and the x-axis. So let's go ahead and set that up. R is the base of a solid whose cross-sections perpendicular to the x-axis are equilateral triangles. So our cross-sections are perpendicular to the x-axis, which means that they're going to be vertical slices or cross-sections. So you can see here this is perpendicular to the x-axis. This time when I pull this cross-section out, when I pull this slice out, it's going to be an equilateral triangle. So let's show you what this looks like. Go ahead and draw an equilateral triangle first. And then behind it, draw two lines that go out. Try to make them as parallel as possible, and then go ahead and connect the two. And this is what we have pulled out. So if it helps, those of you who prefer 3D, you can go ahead and draw in the dots to show the back slice of it. So that is what it looks like. And now we can talk about the side length. So because it's an equilateral triangle and this cross section is x tall, that means this is x right here. So let me show you what we've just pulled out. This piece that we can see on the graph is this piece back here. That is what we have pulled out. So, because it's an equilateral triangle, that means that if that side is x, this side is x, this side is x. How thick is this triangle? Well, similar to last time, however wide your change in x values are. So this is dx thick. So now we need to find the area of this cross section. So what I'm going to do is I'm now going to look at it as a 2D. So I'm just going to look at the face. This is now in 2D. So imagine taking this, we drew it in 3D, now you're looking at it at an angle, you're just seeing one face of it. So we know that each of the sides are x. Now for an area of a triangle, you need half times base times height. So here, your height is actually this distance from here to here. So we need to use Pythagorean theorem on this piece of the triangle in order to find that distance h. We know the sides, but we do not know what the height is. So Pythagorean theorem, we're going to have a squared plus b squared equals c squared. So the hypotenuse here is x, this is c. My height is like my b, and my a is this value right here. So because the whole distance here is x, this distance from here to here will be 1/2 x. All right, so let's go ahead and do Pythagorean theorem. So a is 1/2 x, and I'm going to square that. B is my unknown, what I'm trying to solve for, h. And C is my hypotenuse, that's x. All right, let's go ahead and multiply that out. I'm going to go ahead and, oops, sorry, that's a 4. I'm going to go ahead and subtract 1/4 x squared both sides to combine with this one. So I'll get h squared equals 3/4 x squared. Since this was 1, this was a 1x, so 1 minus 1/4 is 3/4. And once you take the square root of both sides, we are left with square root of 3 over 2x. So square root of 4 is 2, square root of x squared is x. So now I know how high this triangle is. So let's go back over here and let's do the area of just this face. So area is 1/2 times base times height. My base is x. My base is my whole entire length. Remember, I only used 1/2 x just to find what h was. And I know my height is square root of 3 over 2x. So if you were to multiply this all out, we would get the square root of 3 over 4x squared. So now that we have the area of just this one face, we're going to go ahead and find all the areas added up together. So I will do that over here. We are going from 0 to 4. And I'm going to go ahead and take square root of 3 over 4x squared dx. So remember, this was the area of one slice. And so now we are going to find the volume of all the slices by doing dx. So there's the dx, and then adding up using integrals. So for this, just go ahead and practice using your calculator. So we have math 9 from 0 to 4 of, and if you remember, the fraction button is alpha y equals. You can hit 1 there. So that way you can have a fraction, enter into a fraction quite easily. Square root of 3 over 4 x squared dx. All right, that leads us to our formula. If College Board asks you for a region whose cross sections are perpendicular to the x-axis, here's the formula right here. So I went ahead and pulled that square root of 3 over 4 outside of the integral because it's constant. And so we have s squared ds, where s is the side length of the triangle. So in other words, the height of the curve. Here, my curve was x high. So just in general, whatever your S is. All right, let's go ahead and try an example 2. So now R is the region in the first quadrant, bounded by the graph of y equals x cubed, x equals 2, and the x-axis. So x cubed looks something like this. X equals 2 is here. The base of the solid whose cross-sections are perpendicular to the x-axis are equilateral triangles. So again, we're going to go ahead and use this formula. So if you draw this slice, it is perpendicular to the x-axis. And we have that s here, or in other words, my x here is now x cubed. If you would like, you can go ahead and draw the equilateral triangle. However, I'm just going to go ahead and use the formula. So here, s is x cubed. So if I go ahead and use my formula, cube root of 4, integral from 0 to 2, those are my limits, my boundaries, of x cubed squared. So please be careful with this. You need parentheses around that. And you'll notice this one does not say to use a graphing calculator, so let's go ahead and practice our integration by hand. So x cubed squared would be x to the 6th. So I'm going to go ahead and integrate that as x to the 7th over 7. from 0 to 2. So if you go ahead and plug in 2 to the 7th over 7, and you multiply everything out, you'll notice here that 2 to the 7th, when you multiply that out, you'll get 2 times 2 and then 5 other 2's. But you'll notice 2 times 2 is 4, and there's a 4 being divided down here. So you can go ahead and divide out the 4 and the 4. So you're just left with 2 to the 5th in the top, which is 32. Square root of 3 over 7, which is letter B. Okay, so I would like you to go ahead and pause the video right now on whatever device you're using. Go ahead, try this on your own, and when you click play, I will go over it. Okay, so I hope you tried it. This time my slice is x squared high, or x squared tall. So now I have, again, the same formula, square root of 3 over 4. This time I'm going from 0 up to 4. Those are my boundaries. And I'm going to take s and I'm going to square it. So please, again, just like up above, make sure you're using parentheses. Again, this one is not calculator active. So x squared squared would be x to the 4th. So if we integrate that, that'll be x to the 5th over 5 from 0 to 4. And again, we have a similar situation that when I plug in 4, there's 5 4's here if I multiply this out, and there's a 4 here, so it would just be 4 to the 4th, which is 256. And that 1 4 would have divided with the other 4, so just left with the 5. So that is, again, answer B. Okay. Now this time we're going to move on to isosceles triangles. So again, I'm going to set you up with an example that will lead us to the formula. So again, I'm going to use y equals x, but this time we're going to go up to 5. And so this time it says that my cross sections perpendicular to the x-axis are right isosceles triangles with a leg in the region R. What is the volume? So if we draw our slice, again, it's perpendicular to the x-axis. Let's pull it out. This slice is x tall. Its thickness is dx. If I were to pull it out, a right isosceles triangle, isosceles meaning that these two sides have the same length and it's a right triangle. So this time when I pull out my slice, it looks something like this. So to make it 3D looking, you can draw two lines going backwards and then just connect the two. And this is dx thick. Obviously, this is not a great 3D image, but I hope you get the picture. Okay, so these two are equal length. Let's just find the area of the face of the triangle. So it's 1/2 base times height. We do not have the same situation as up here where we needed to find the height. We actually know the height and the base are the same, so it's both x. And then to make it into a volume, like a pyramid, we would times it by dx, and then in order to add up all these slices, we would take the area. So you would take the area from 0 to 5, 1/2 x squared dx. And so you can grab your calculator. There we go. Grab your calculator, math 9, 0 to 5. 1/2 x to the 2nd power dx. Whoops. And you would get 20.833. Okay, so that leads us to our formula, but I'm going to go ahead and head to another video, so go ahead and click on the next video to see the backside.